nuclear reactions. A nuclear reaction takes place when a nucleus or a particle collides with another nucleus or particle, and a change occurs in the nature of the nucleus or the particle. So, for example here, we have an alpha particle. It collides with a nitrogen-14 nucleus, and the result is an oxygen-17 nucleus plus a proton or a hydrogen nucleus. Here in this case we can see that the electric charge 2 plus 7 equals 8 plus 1 is conserved. The nucleon number 4 plus 14 equals 18 is the same as 17 plus 1 is also conserved. And we also know that mass energy, linear momentum, and angular momentum are also conserved. There are two ways to write a reaction. First of all, we can write it, as you can see here on the left, A plus X becomes B plus Y. Here, A is a bombarding particle, X is the target nucleus, B is a product particle, and Y is termed the recoil nucleus. Another way of writing this, although we won't use it, is to show the target nucleus on the left, the recoil nucleus on the right, and the particles involved in the reaction A and B contained in parentheses in between. There's also a reaction energy known as a Q value. It's the energy available from the difference in mass of the reactants and the products. In other words, Q is the sum of the reactant masses minus the sum of the product masses. Ma plus mx minus mb minus my. We multiply this by c squared using Einstein's relationship to get the mass defect, the difference in the masses, multiplied by our conversion factor of 931.5 million electron volts for each unit. Since mass energy is conserved, the Q value is equal to the change in kinetic energy. That is, the Q value is equal to the difference between the sum of the kinetic energies of the reactants and the kinetic energies of the products. Q equals KEB plus KEY minus KEA minus KEX. If the Q value is positive, the products have more kinetic energy. That is, energy is released in the reaction, and this reaction is said to be exothermic. More energy is put in than is released. On the other hand, if Q is negative, the reactants have more kinetic energy. Energy is absorbed in the reaction. The reaction is endothermic. More energy is put in than is released. There's also a threshold energy. This is the minimum kinetic energy between the reactants in order for any reaction to take place. Let's do an example reaction and try to establish whether that reaction is exothermic or endothermic. Here we have a deuterium or hydrogen-2 nucleus interacting with nitrogen-14. The result gives us a helium-3 nucleus and something else. So first let's find that something else. Now, one thing we know is that the total Z, or total atomic number, is 8. Here we have only 2, so we must have 6 on this particular nucleus. In addition, we started with a total atomic mass number of 16. We have 3 over here, so we need 13. And if we go to our periodic table and look up atomic number 6, we find that that's carbon. All right, now that we've got all that, we can look up the masses of each of these isotopes in an isotope table. And what we find is the following. We're going to start over here with our reactants. We have a mass here of 2.014102 units for the deuterium, another 14.003074 atomic mass units for the nitrogen-14. And then On the other side, we have our helium-3 with this 3 plus amount of atomic mass units, and then carbon-13 with 13 plus atomic mass units. When we take the difference between these two, we find that we started out with less mass and ended up with more mass. So the mass defect is negative 0.002207 units. That means that we've got to put energy in. But let's go ahead and calculate that. If we use Einstein's expression for mass energy, we're going to find the total amount of energy involved here. Well, here we're going to convert our atomic mass units to kilograms. So we're going to multiply by the speed of light squared in meters per second squared, and we're going to get a total amount of energy required to make the reaction take place of negative 3.294 times 10 to the minus 13 joules. So because this energy is negative, it means that the reaction is endothermic. It turns out that neutrons are very effective in nuclear reactions. Because they have no charge, they're not repelled by the nucleus and are much more easily inserted than charged particles. Because of this, physicists are able to create transuranic elements, that is, elements with a greater atomic number than uranium, by neutron bombardment. On the picture on the left, you can see the chain of nuclear reactions that start with uranium-238 absorbing a neutron and subsequently decaying and becoming plutonium-239.